characteristics of linear regression, right, in terms of the line of best fit. Right? In a similar way, if you're only dealing with a single set of variables, right, a standard deviation represents how far away on average is any one point from the mean, right? That's what this is calculating. Okay. For a line of best fit, you're essentially calculating how far away on average is any one paired set of scores from the line, right? So it's got a similar formulaic presentation using the sum of squares. It's trying to minimize the distance between, if you're looking at one variable, a single point and the mean, and with linear regression using two paired scores, how far away is that paired set of scores from the line of best fit? And since you're trying to minimize that overall distance, that gives you the most effective line mathematically.
Okay.
Right? Linear regression assumes two sets of data, x and y. Assumes an underlying linear relationship, not curvilinear, right? So no exponents, right? Not multivariate, right? Not dealing with an x, y, and a z. Linear regression allows prediction. You know 1x, you know the x, you know the line of best fit, you can make the best prediction for y. So he's talking about, I think when you came in, essentially saying, I'll start back to saying that stuff. If you have IQ, and you only have that one variable, if I draw a person from the population at random, right, what would you predict their IQ to be? Best guess.
100.
100. Why'd you say that?
It's the mean, it's the average.
So mean it's the average. It's also the most frequently occurring score. That's why the curve's top peaks out, the middle features, right? If I know another characteristic about the person, right, like their GPA in high school, or their GPA in college, or their ACT scores, or their SAT scores, right, or their income level, right, or any number of 1,000 other variables. If I know any other variable, let's call it y, right? Actually, let's call this one x. Create the variable x. Let's say, for example, I know a couple of those variables, and I use almost the same example wherever you're coming in. If, let's say, I find a person, and instead of picking them at random from the population, I pick somebody who has a 4.0 GPA in high school, 4.0 GPA in college, right? They graduate with honors in college, right? They go on to a successful career and make a ton of money that year, right? What's your best prediction of their IQ?
125 or higher?
You would say 125. You would simply say higher than 100.
Higher than 100, okay.
Right? You can't get to the 125 specifically without knowing those actual data.
But it's above
If you knew the actual math, you could pinpoint down exactly where that point is. But it's going to be higher than the mean.
We know
right?
it's above average, right?
Because you have more information about that individual. You have more knowledge of variables. If I only have one variable, that's my X score, right? That allows me to make a slightly better prediction of Y than simply guessing the mean. Right? So the more data I have, the more accurately I can make those predictions. And that's where we get off the topic of AI predicting your futures and lives at this point. Because it will.
Yeah.
Oh goodness. Anyways, if you have the question like, what's the percent of people with IQ between 125 and 140, when you get the Z-scores, you use the B column and you find those, and then what? And then you subtract them? Subtract the smaller one from the
There are a lot of ways you can do it. Right? At least 4 relatively common ways.
What's the easiest?
The simplest tends to be, for most people, using either both B column, well, both B scores, one from the first variable, one from the second variable,
Yeah.
right? Or both C columns,
Oh, okay.
right?
So you can really use either one?
As long as you're consistent.
Yeah.
As long as you know what you're doing.
Okay.
So for example, let's just do that one. If I say, what's the percentage of the population between 125 and 140 IQ? Got 125 here, right? That's this data point, right? What else would you do if I wanted to find the percentage between 125 and 140?
Find the Z-score for 140.
Find the Z-score for 140, right? Same formula. Give me a 2.67. Right? For the sake of argument, just to make this more consistent with what I have on the board, right? I started with the C column here for 125, right? The 140 falls somewhere out here. It's 2.67. I now want this area between those two. I'll double hatch it this way. Right? Let's use the C column, since I already got C column data here. Right?
Okay.
This value is a C column, right?
Mm-hmm.
The 0.475.
Mm-hmm.
What is the C column associated with a 2.67 z-score?
0.0038.
So now I've got number for C, number for C. How do I get this area that I've double hashed?
Subtract the 0.475 from the 0.038.
Other way. Yes.
Wow,
Subtract the
okay.
smaller one, the
From
0.038, from the larger one, the 0.458.
And as always,
So
subtract the largest and smallest from-
0.0475 minus 0.0038.
Oh, that's how I said it in my head. Okay.
Mm-hmm.
0.327, I think.
What?
I think I-
0.0437. What am I crazy?
I can't answer
Should
that
we do it
question.
the other way?
I can't answer that question.
No, I know, that's right, it's right. 0.0437. I'll make sure I didn't put it wrong.
Yeah, 0.437. Sorry. Oh, that's what I did. Okay. 0.437. Notice that used the C column. Sorry, you got the C column here.
Uh-huh,
If I wanted to use the B column,
okay.
which is where most people tend to intuitively start, I don't know why.
Cause I think between and B, like I use the B column for between.
Cause,
I don't know.
cause B says area between mean and Z.
Yeah, but it's not the mean.
So the larger area here is gonna be the 140, right? And that's gonna be a,
0.4960.
0.4960, yeah. And then, I'll do that underneath. The 125, right, is gonna be a 0.4525.
Yeah.
Mm-hmm. Okay, I think that may.
Take the bigger one. Take the bigger one,
Okay.
subtract the smaller one, because you're looking at the larger area minus the smaller area to give you what's left over, right? It'll give you the exact same value.
That is crazy. I just unlocked while I was having like struggling.
Yes.
I would use
See,
the B
he
column
told
for
you.
one. I would use the B column for like a between and maybe like the C column for the other one. It would always get it wrong.
You can do it that way if you wanted to.
So you could use a B. You could use a B for one and a C
Yes.
for the other.
I'll do it this way, show you. Same curve, same 2 points. Same locations, right? Same exact area here,
Mm-hmm.
right? If I take the C column for the 140, the C column for the 140 is the 0038,
Mm-hmm.
right? So this area right here, 038, same as it was here.
Right.
If I take the B column for the 125, right, the B column for the 125 is this value, the 4525. That's from there to there, right? If I want to get this area using these two numbers, how do I get it? What's the total area from the middle all the way up, from the mean up?
50%.
The whole thing must be 50%, right? So if the whole thing from here to here is 50%, and I want to know this area,
You would.
knowing that one and that one,
You would subtract both of those from 50%.
add those two together and subtract them from 50%.
That's why I used to mess up, then, because I just used to subtract them from each other. Thank you.
So
I'll stick with
I gotta
this.
go,
Okay.
but thanks for
Nothing.
helping. No, what?
Bye. You know I gotta mess with you, Reed.
I'll see you next week.
See you.
Real life practice, could you take like the 140 from the 125 and then like take a group of the data between those numbers and still get it?
You cannot.
Hello.
Here's a question. Why not? Why not? In other words, if you took the 125,
Like if you,
subtract that from 140, you get a value of 15, right?
yeah, like you would take, so like when you're doing like a sample data or population data, when you're getting your averages, say, say on the homework or whatever, say you had numbers between 125 and 140, and you just took those numbers and used that as your average underneath.
Oh, you would essentially be using a different underlying distribution, right? It would still be a normal, you'd still assume it's normal distribution, right? But if you have a limited subset of your data, right, that will essentially change the window in which you will make calculations. Let me give you an idea. I hesitate to do that. It might go on here. All right, I'm just going to encroach on material we're going to get into in the next couple weeks. Okay. Suppose I have a bag full of lottery ping pong balls. I've got a bag of lottery balls. Okay? But unlike the lottery, I limit the number of people. In one of the bags, right, I have values on the ping pong balls from 1 to 10. Okay? It's the only values I can take out. Doesn't matter how many ping pong balls I got, right? I have 100 balls with 10 ones and 10 hundreds and 10 eights and so on. Right? So a lot of ping pong balls in it, but the only values we can take are 1 to 10. I got another bag. It goes between 1 and 1,000. Okay? I start drawing balls at random out of the ping pong, out of the bags. Right? The numbers I draw are 5, 9, 2, 7. Right? Which bag did it come from?
The first one.
Either one. Either
Yeah,
one.
that was a good question.
What's that?
Could've came from
Probably the first one, only because it's a
Better
better
answer.
chance.
Not the first one, but
Mo-
probably the
probably
first one,
the first
right? Because this one has those numbers in it, right? You could have drawn
But the
those 4
likelihood-
numbers,
the
but the
likelihood-
probability of drawing these 4 numbers, given the 1,000 you're choosing from, is incredibly small, right? Probability you're coming out of this bag fits the distribution you expect, right? Make sense?
Yeah,
Now,
because of this.
you're picking people out of the population, right? Everybody you pick has an IQ score between 125 and 140. Right? Every value you get 140, you get 137, you get 135, right? Are you drawing them from a larger population, or are you drawing them from some special population that's a special bag?
Special population.
It's probably a special bag, right? Does that make sense? We may come across similar topics to that in a couple weeks, because that starts getting, we're not doing this for this test, but that will get into things like inferential statistics. You're making judgments based on probabilities. And the likelihood is, if I draw these numbers, that they came from this bag, not this one. Because the probability they came from this bag is 1 in thousands, right? The probability they came from this bag is right at about 50-50, right?
Good explanation.
I was thinking, did you do that to find your Z-score though?
Yes. Yeah. You actually have raw data, right? If I give you a set of raw data, and you assume an underlying population, right? Okay, I'll give you a real world
When you
example.
asked between
Play something.
125 and 140.
So you would remember
No,
this
you
for
wouldn't
the
ask me
test.
if I give you a raw set of data, you would then calculate the mean based on the sample distribution. If you assume a normal distribution, right, and you assume the standard deviation based on the sample you got, you can make probability assessments based on the limited number of data you got. We give a quick example. This actually happened back in World War II. Back in World War II, when the Allied soldiers were rolling out and engaging with the Axis forces at some point, anything that had a number on it, right? Piece of a motor, right? Piece of a tank, right? So anything that has a serial number on it, right? If you're so you collect that data, right? You hang on to that piece, you send in that information. At one point, there's a battle coming up, and the Allied officers in charge are trying to estimate the opposing forces and estimate how many tanks they were going to have to come across. Right? They're going to try to estimate the number of opposing forces in terms of tanks, so that they would know how to put up their own battle lines, how many tanks they have to put up their own, how to engage them most effectively. Right? Preceding that battle in that area, soldiers had collected four pieces, right, of little components, same component, from 4 different tanks, one piece from each tank, right, that had a serial number on it, right? And the Allies had rumors, they had reports, they had speculation, they had gossip about how many tanks were supposed to be there, and some people traded them. They gave those numbers, 4 data points, right? Because they're statisticians, right? Statisticians use that data as a sample, right? Calculated a Z-score, right? And gave the people in charge the probabilities associated with any number of given tanks that are going to have to come across. Based on, if you pick these pieces up at random, what's the probability you get? these 4 serial numbers, right? And the statisticians nailed it to within like 1 tank. They're able to predict how many tanks they're going to come across based off 4 data points,
Damn.
right? And z-score distributions. So the story goes. I've only seen that reported in 1 location, so I don't know how confident I am in that particular story. But yeah, you can use that data.
So stats go way, way, way back.
And not really.
Well,
This kind of stats, this kind of data, 1920s, about 1919, 1920 was when Fisher and Pearson were doing most of their statistical contributions. All right, so what else for tests? Any questions on t-scores? Is that all right?
It's a good foundation for me. So would it either be 1 score or 2 scores, and we'll figure it out just like that?
If you're given raw data, you have to calculate the standard deviation, calculate the full z-score calculation.
Let's do one of those. What the heck?
Well, we can, it's not a problem.
Okay.
But I want to make sure I cover the broad information on the test and not just focus on the z-scores.
True. So we can go to like slope stuff just in case somebody else do have to leave pretty
You want to
soon.
do that, flip it around, come back to z-scores at the end? Somebody need to do linear regressions? Come up with linear regression.
I would like to see one example of everything. That's just me. You know, just so that I can have like a little study sheet for the.
Alright, so let's use a limited set. Suppose you go to your local representations of department stores and you look in, how about the makeup section? And you count how many offerings, how many individual, let's say, shades, colors of nail polish in their makeup section, right? And in one store, let's say they got 120, in another store they've got 80, in another store they've got 300, in another store they've got 50, right? Just use 4 data points, make it relatively straightforward. Could be 10 stores, could be 20 stores, right? Any numbers, X values, right? Assume this sample data is representative of a normal distribution, normal population, right? What is the percentage of stores you would expect to find that have more than 150 offerings for nail polish?
So we gotta draw it first.
What percent greater than 150? You can draw first if you want. What's the mean?
Would it be all of them added up divided by 4?
Yep, which is
Okay. What is it? What is
550 is the summation of X.
divided by 4?
Divide 550 by 4, and you probably get 130.
37.5.
Yeah, that'll work. 137.5. That's the mean for your X score, right? What's the Z score associated with that? What's the Z score that corresponds to the mean for any distribution, for any Z distribution?
0.
0. The 150's here, right? In order to calculate more than,
You won't see.
I want C column, right? But in order to get the C column, I have to calculate the Z score associated with the 150, right? So how do I get the Z score? Here.
You have to use you just said that was a population, right?
No, I said, assume this is a sample,
A sample, okay.
which is representative of the population. Population, saying it's representative means I can do this with it. I can use the Z-score population data as if it's representative, right?
So you'd have to use that one with the S in there. The
Yes.
Z-score with the S. So it'd be 150 minus the 137.5. No.
So A minus the 137 divided by S, right?
And then S would be
What's S gonna be?
sample 4.
Huh?
4?
That's the number of scores, that's N.
We'd have
If
to
I
add
don't
it.
have this specifically, I'm not giving you the standardization,
Oh, it's S equals all of that.
you can
Okay.
use this, plug in here,
I'm
Right.
glad you caught me. That would've been a
which
quick.
means you're gonna need a bunch of X squared scores. This is the other first thing. And this one, the first thing you do is draw it. If you're given a raw set of scores like this, I would recommend the first thing you do is square all the scores, get the sums, and then draw it after that. So a couple first things you can do. I'm gonna do it. So squaring this. Gives you those values. Let me move my X.
Did you specialize in math or psychology?
I'm decent at math. I know people who are way better.
Says the AI.
I know people who are way better. There was a guy in India just recently who broke 15 Guinness Book of World Records for calculations. He was able to calculate in his head a number of different calculations, like something like I think 15 5-digit numbers added together. He was able to calculate the answer in 30 seconds. And he was doing advanced multiplying like two 15-digit numbers by each other in his head, getting an answer. And in times, it broke the world records. He's got a list of like 15 Guinness records. But basically, it's a list of, here's your, let's say, 8 6-digit numbers, or 5 10-digit numbers, or 16 3-digit numbers, adding them together, multiplying things together, all kinds of stuff, getting the specific answer. Human brain's an amazing thing. Your brain can calculate, your brain can do an intense number of calculations incredibly well, right? With
Yeah.
practice of the right synaptic connections, but most people just never train for it. Most people never don't know how to do it.
So my kid's gonna be a genius.
Hopefully.
Do you ever do that one method where they count like
There are tons of methods.
their fingers?
That's an older one, that's been around for 80 years or something. No, I never learned how to do that.
I learned how to do this January, February, March, to see if it's 30 or 31 days in it. With the
No,
numbers.
just say 30 days have September, April, June, and November. The rest have 31, except February that has 28. Unless it's a leap year, it's 29.
Did you learn that in school?
Yep.
There are any number of mnemonics people can use. The interesting thing is with math in particular, a lot of musical stuff, sometimes people that do foreign languages and polyglot kind of stuff, even scientific kind of stuff and formulas and so forth, they don't have to put it into those kind of equations. Their brain simply computes it and picks up the answer.
My brain picks it up and spits
Right,
it out.
so
Can we do the correlation?
Oh,
One correlation.
that was 1,000. My God, that was 113,300.
100, what?
113,300.
Okay. Put a little comma here. That's not a one, that's a comma. Right? So, if I've got 12.5 in my numerator, what goes in the denominator? Plug in values.
This equals. Oh, gee.
There you go, B. What value
Isn't
plug in
that
here?
for-
Oh, 113,300.
What?
Minus
550.
550 squared.
Don't forget the square. What's n?
4.
What's the denominator to denominator?
4 minus 1.
3. Yep.
What am I missing? it's a common thing people tend to miss, so don't forget it.
The square root?
Radical sign. There, all they are. Right?
My question is, oh, no, got it. What is, N is what again? N is 4.
4.
I think
What
that's
does
right.
N stand
3025? 00?
Let me see.
N is equal to 4, because I got a sample size of 4.
302,500, you're right.
That's squared 550 in my head. I can teach you a trick for that.
So there.
Point 1562.
That's 7518. Something.
Yeah, I don't have the calculator. Well, I can Google one.
Oh, he's prepared. He got his calculator this time.
Here.
Ah, I missed it. Look at this one. I'm just gonna round that to the whole number, 12558, instead of dealing with the decimal at the bottom of it. Oh, alright, that's fine. Don't forget the routing sign, I sometimes leave it off myself just because it's easier for me to put it on at the end.
That's what I was gonna ask you, is it not square root?
If you don't draw it all the way through, you draw it at the beginning, and you remember to take it at the end, I'll be fine with that. But technically, if you wanna watch a transcription, you wanna put the radical sign in every step. I frequently don't, after we do all the calculation, then drop the radical sign the last second.
That is an 8, or you round and you get
Where, here?
12, yeah,
12558. It's actually 12558.33 or something like that.
okay, so 12,
I just rounded off to the nearest whole number because it won't make that much difference. And 6 significant figures. Put that 111 over here. Something to remember. What is this number? What is that number? It's a Z-score. Right? So to draw it, it's 0.110. For our purposes then, because the Z-table only has 2 values, we'll say 0.11.
And even if we put the 0.33 on the,
It'll still be 0.11.
okay, cool.
Yeah, it'll, within rounding error, it's gonna be almost exactly. It might, if the rounding error tips it exactly the right way, be a decimal point higher or a decimal point lower, but I expect it to be the exact same value.
So 12.5 divided by,
So the Z-score 0.11. Right.
0.4562.
Correct. More than 150. 4562. Which is the original question, right? What would you estimate? What percentage of the population of department stores have more than 150 offerings of color for their nail polish? And you get 45%, 45.62%. Leave that as a whole 4 digits, right? 4562, If you convert it to a percentage, use 2 decimal points, 45.62%.
So you have to keep the radical percentage even after you find the square root?
Oh, yeah, no, you're right. I had one extra. I was just checking them off, didn't realize it already done. So that comes out of that.
Okay,
Yes.
I'm just making sure.
You're good. You don't take the radical sign twice. You don't take the square root of a square root. It could be a quad root. There are no quad roots in the statistic we're using.
So square. So basically, the final step is when we finish with the square root.
Well, once you take a square, you have to divide the numerator, in this case 12.5, by the denominator, which is your standard deviation. Your standard deviation is 112. Right?
Mm-hmm.
Quick check, if you want to. It'll be a little bit marginal here because I only have 4 data points, but your standard deviation will, in general, be approximately 1/3 of your range, right? So what's the range over here?
37,
No.
137. Oh, the range would be the highest versus minus the lowest.
Which is
300 minus 50.
just 250.
Mm-hmm.
Now the 112, it's in the hundreds, not really close to that, right? If I had more data points for my sample, it would get closer to that 1/3.
Mm-hmm.
If the sample were exactly equal to the population data, right? When I say it's approximately 1/3, it's actually technically 34.13%, because that's one standard deviation for a normal distribution. That's the column for one standard deviation, 0.3413. You should write out 1/3 be 33%.
So there's not gonna be a time when we have to figure out the standard deviation by ourselves. Is it? Not
In this case, it's part of the bigger equation for the z-score.
Okay. Okay.
Alright, you can do linear regression if you have the time.
Yeah, we got a few minutes, sure.
Okay.
So here's the z-scores, move on. We can get rid of a bunch of stuff up here then.
You think you'll be able to be here for Cameron at 3:30? I mean at 3:10?
I will probably be here. After this, I have another thing scheduled. But if she wants to come by, she can. I'll be here. I'm not sure if she needs anything specifically. All right, so linear regression. She's trying to predict, in this case, a y-score from knowledge of an x-score. If you didn't have the x-score at all, if you're trying to predict a y, you simply predict the mean for y. Right, it's your best prediction because that's the most frequently occurring score. If you have one other variable and there are paired sets of scores in your sample, it gives you a little bit more information to potentially make a better prediction. Right? So let's say. I'll do it this way. That's some big numbers. Well, I can throw it out. Now, I'm running through some numbers in my head and trying to think of some paired scores. But it's okay, something maybe from psychology. Let's ask. Go out to population, collect a sample of individuals, and let's say that from the sample of individuals, you're taking multiple pieces of data. I'll see one for the 210 class. You ask the individuals something along the lines of, how many motorcycle accidents have you been in your life, right? And you also ask them, how many tattoos do they have? Remember that example from the 210 class? That's one of the examples I give. They're actually related, they're correlated to each other. If they're correlated, right, there will be a line of best fit predicting it, right?
How are they correlated?
Huh?
How, right?
These two things are related to each other,
Okay.
right? Line of best fit allows you to predict one variable and knowing the other variable.
Okay.
Correlation is essentially asking what is the degree, what is the measurement of the association between the two variables. If you know the degree of association, you can calculate a line of best fit. If you know the slope of the line of best fit, you can calculate the correlation.
Okay.
We aren't doing those interchangeable formulas. There are formulas that will swap these two things back and forth,
Oh,
right? So you got the slope for both lines. A slope predicting x from y and a slope predicting y from x. You can put those together in a ratio to create the correlation. That's not something we're gonna do. So, we're gonna have an x score, y score. X, let's say, is number of tattoos. Right? Y is number motorcycle accidents. Okay? Since person, how many tattoos you got, how many motorcycle accidents you've been in. And you come across, let's say, an individual who's got 5 tattoos, and we'll say they got 5 motorcycle accidents. And somebody else has got 0 tattoos and 1 motorcycle accident. And somebody's got 10 tattoos and 8 motorcycle accidents.
2 tattoos and 1 motorcycle accident.
Huh?
I said 2 tattoos and 1 motorcycle accident.
That'll throw it in there. Doesn't matter to me.
Dang, 15 seems crazy. It's like,
They're klutz too. Alright, so say we got those numbers. Right, notice those are all parent set scores. If I say you come across an individual that you know has 12 tattoos, question is, how many motorcycle accidents do you predict they've been in? Right, so you come across somebody who has 12 tattoos, how many motorcycle accidents do you predict they have been in? From this data. This data may or may not be representative of the actual numbers, I just made it up, but it should at least show a trend. You can, you can do the calculations regardless. Right? The numbers don't care where they came from. Right? The math the math doesn't care where the numbers come from. You just plug in the numbers into the equations correctly. Does that make sense? You have 2 sets of data. You want to predict, in this case, the second one from the first one. Predicting y from x. So what do you want to do first?
go ahead and get all those x squares and.
You want all the weird
Yeah.
little terms in there, all the square terms, right, plus the xy term. Doesn't matter what order the table goes, let me move this over slightly. So the original here is gonna be twelve tattoos pretty motorcycle accidents. There's x squared, here's y squared, notice you're gonna need xy as well.
Will you have this like already kinda on the test?
For one set of stuff, yes, for another, no. So you'll have to do it at least once.
Oh, but I'm saying you'll already have like x squared, y, you'll already have the columns made for us? Or is
No.
this something that
I'm
we
just
have
gonna
to
give you the raw
remember to
data
do?
and you're gonna have to calculate columns at least once. I'm not gonna have you do it more than once, because I assume once you can do it, you get it correctly. I will, some of the problems, I will give you all the tabular values. Because otherwise it's just eating up a lot of test time you guys should do.
Yeah.
So
more efficiently.
remembering, so I'm trying to remember what I need to do this for. This is for linear regression
Yes,
Yeah.
and correlation coefficients.
and correlation coefficients. Okay.
So how did you get X, Y? What is X, Y now?
How to get what?
Never you mind.
This one?
Never mind, I just figured it out when I was writing the numbers.
Okay. XY comes from multiplying the X term times
Yes.
the Y term. All the way across. So 5 times 5 is still 25, just like it was 5 squared, 5 squared. 10 times 8 is 80, 15 times 10, 150, 2, 1, 2,
Yeah.
4, 6, 24. Right?
You got it right. Well, I need to check the last one, but,
What, 281 for the last one?
yeah, check the last one. 281.
Oh, that's why I did it. So anyway. So what next? Those are all in tabular values, right? If you want to calculate a linear regression, what's the first thing you have to calculate?
Slope.
The slope, the B term here, right? You won't have the term B in front of it, you'll have that equation. So that equation then sets up as, I'll redraw the equation. Which then sets up function x, y is gonna be 281 minus the 36 times 31. We got 6. Yep. Function x squared. So you should plug in numbers there. Start plugging those numbers. Let's see where I got those numbers to plug in.
Yep. Straight from the data.
So without doing a whole bunch of the math, so 95 there. There. We'll round it up a little bit. So we'll say 0.62. That's my slope.
Wait. I thought slope was, okay, see, I would have been messed up. Oh, so that is slope, but to find that B, you have to do all of that.
To find that B, you gotta do that entire equation. All right.
Dang, okay, I need to, okay, so let's see.
Notice it's a positive slope,
Mm-hmm.
right? Which generally means what?
Line
Positive.
going up,
Lines
Like
going up,
to
which
the
tells
right.
this original data what is what?
that predicts the more, what you call it?
As the number of tattoos goes up, the number of motorcycle accidents will also go up.
Yeah,
Okay? So if that's the slope, what else do I need to calculate my line of best fit?
See.
X,
No,
no, what's A?
That's what you need the Y intercept.
The A, okay, I was missing.
It's the y-intercept in this case,
Y equals.
right? How do you get the y-intercept?
By plugging in
Plugging in the B.
B.
You plug in the B, do the line over here. Here's my general equation for a line. So I'll put the equals, the B was the 0.62. Is it? I mean, something for x, something for y, solve for a. What do I put in for x and y as a pair of terms?
Oh, whichever one is, oh, I'm sorry.
The summation of x, summation of y, what? When you said,
A mean, right?
36 6 and
x, you want the mean, right? The mean for x, for 36, divided by 6, which is 6. Right?
36.
So the mean 6 for x, that's gonna be the x squared, x bar here. Mean for y is 31, divided by the 6, right? Should be 5.17.
Backtrack for a second, how did you, where did that, dang, I can't talk, where did that 6 come from?
It's the mean for x,
Okay,
X bar equals 36 over 6, which equals 6.
okay,
Mean for y is y bar, it's going to be 31 over 6, it's going to be 5.17. That's going to plug in this equation. Mean for y, b use calculator is 0.62. Mean for x, right? Solve for a. Or if you want, you can go simply a equals 5.17 minus
3.72. Where'd the 5.17 come from?
31 divided by 6.
mean for y, mean y bar. So you get a equal what?
It's 1.45.
So 1.45.
So 8. Okay.
So now I've got a slope. I've calculated slope with their intercept here. The general equation for the line
Did I miss a step? We got the 1.5, 1.45 from doing what?
1.45 is the y-intercept.
And the y-intercept is.
You solve for the y-intercept by plugging in mean for x, mean for y, slope, solving for a. Right? This equation. Plug in this value, plug in this value, plug in that value, solve for the one you don't have.
Oh, so after
If
you
you
solve
solve
it.
for it first, this is the equation you're solving for, but you're still plugging in these three numbers.
Okay, got you. Check.
That'll give you the 1.45.
1.45.
So this is the equation that best predicts line of best fit.
So that would be the answer.
Dang.
One more step. Because the original question was not calculate line of best fit. The original question was, how many motorcycle accidents do you predict?
12.
From 12 tattoos, how many motorcycle accidents you predict? You plug in the 12
For the
for
X.
X. And you predict 8.89 motorcycle accidents. That becomes the correct answer to the original question.
Did you round up in the case of
No.
car accidents?
No. In this case, leave it exact, it's an exact value. Technically, you cannot have a decimal point value of motorcycle accidents. But one of the assumptions behind the linear regression is both X and Y are continuous, right? Even though in the real world, tattoos and motorcycle accidents are discrete data, right? And so yeah, you leave it as an exact prediction. So that's the prediction you would have. But yeah, technically you probably run it, you won't say down, but leave it as an exact prediction.
Where'd you get the decimal answer from again?
Where do I get the what?
8.89.
I plug in 12 for X into the least squares regression line. So down at the bottom, where I've got the Y equals 0.62X plus 1.45, plug in 12 for X, solve for Y.
Then you find R with all of the answers or the.
If I said, what's the correlation coefficient between number of motorcycle accidents and number of tattoos, right? How do I do it?
You just plug everything in,
You know what?
the equation for R.
Would you have to plug everything in at this point?
I'm not,
If I said, what's the correlation coefficient, or say, what's the degree of association between motorcycle accidents and tattoos? So I'm not giving you a specific number, right? There's my equation for correlation coefficient. But I've already done this, right?
So
My slope. So the numerator is still 95, because that's the exact same thing as this, right? I've already done this block, right? So this part of the equation is 154. I need to calculate the y sum of squares, right, which is this part of the equation, because I haven't done that yet. But notice I haven't used the tabular value for y yet anyway, because I need it for the slope if I'm predicting y from x. If you're predicting x from y, you would. You'd use this one and not this one. Right? We didn't do that in class, I'm not supposed to know that. But at this point, you simply plug in the don't forget the radical sine of everything.
But you will be asking us the R?
I will give you, you will have to calculate our equation. On the test, it'll be set from the linear
And it's called correlation or degree of
association,
association?
right? There are multiple degrees of association you can take, you can calculate. Right? One of them is a Pearson product moment correlation coefficient, which is this one, R. So correlation coefficient is a degree of, measure of association, right? And it will come back with a number between -1 and +1.
Hey, Cameron.
Right?
Okay, let me tell you real quick. So he is still here, but he said at 3 o'clock he had something else.
Well, it's not through in that range.
He said around.
I'll
that
be here
time.
for a little while. She wants to have any, if she has any specific questions.
He said that he'll be here for a little while if you have any specific questions, but you're coming from afar. If you have any specific questions, I mean, probably still, maybe ask him if we could do a Zoom or something like that one day this week, okay? Could you do a Zoom with her one day this week?
Easily.
He said it won't be easy.
Well, Tuesday I got class all day. Oh, this week, maybe this week.
Oh, he
Said
said
probably
maybe,
next
he said maybe this week. He said maybe this week he would be able to. He thought we were talking about next week. So he said maybe this week you'll probably get on Zoom with him and ask any questions you may have. Or maybe even call him.
Ask her to email me.
He said email him.
So it's next Tuesday
Okay.
when we're having the test?
Okay.
Yes.
Okay,
So
he said
actually,
email.
I thought about it because of my vacation. I should be here next Tuesday, so I'm just gonna
Okay,
take
no problem. Then
my
I'll send you
test
my
next
notes too.
Tuesday.
Okay.
We talked about taking it today.
Yes.
But then I looked
Okay,
at my
girl, take
schedule, I was
care.
like, I'm gonna be here
Don't worry.
Tuesday.
Okay,
so-
okay, bye-bye.
I'll give you 2 more days. So the sum of squares for y is 66.84. 66.84 times the 154 gives me, let me move this down here. Let's go around that 67. I get approximately 0.93.
Could you do me a favor and go back to that 5.17 equals 6.2, I mean 0.62 times 6 plus 8? I just tried to, I
Not sure
guess,
where you're at.
over there on the other one,
You gotta,
right there.
put in the
Yeah.
12 for the X.
So, go up one. Okay, so solving for 8 to get that,
You plugged in these 3 values. You've calculated the slope. You know the mean for x and y. So you're plugging in the mean for y. The
Yeah, I'm
slope
past
calculated.
that part. I'm past that part. I guess I did it wrong.
Solving
him?
for x, solving for a, use your 1.45.
I'm supposed to multiply both sides by 0.62 divided by 6, right?
No, not initially.
Okay.
Initially, you would subtract 1.45 from both sides.
Okay, so I
Oh,
need to get 1.45.
Subtract it, if you wanna do it this way. Take the 0.62 times 6, get a value.
7.44.
No,
No.
0.62 times 6 will give you a value of about 0.3 or 3.6.
3.72. Okay.
Yeah, so 3.7. Take that 3.7, subtract it from both sides, so 5.17 minus the 3.7, right, and that'll give you the 145.
Okay, I divided it on both sides.
That's moving around algebraically.
And I guess I divided it because I multiplied that, but that's what threw me off. Okay, I see it. Basic algebra. The multiplication threw me off, I guess. I saw multiplication and division
So my correlation coefficient, given this original data we made up, comes in at a 0.93, which is incredibly high as a correlation coefficient. Still well in the ballpark because it's less than 1, right? But 0.93 is really close to 1, so there's a very strong, from this data, from the sample, mathematical relationship. There's a very strong degree of association between number of motorcycle accidents and number of tattoos. That's a 0.93. If I want to predict, right, one from the other, for what purpose of our class, if I want to predict number of motorcycle accidents from the number of tattoos, I can plug into this equation. Is that all right? So what are the questions?
So after finding that little part at the bottom, even if you ask us 10, we just plug in 10. And it's the same, we don't have to do any extra work since we've already found the line
Right.
that's fit.
Recognize what the units you are dealing with are. So for example, X is number of tattoos the person's had in their life. Y is number of motorcycle accidents the person's had in their life.
Big difference.
If I changed it to something like X is number of motorcycle accidents the person had in the last decade, right? And Y is the number of tattoos the person's had in the last decade, right? Assume the decades in their life are equally represented and continuous across their lifespan. If somebody's had, let's say, 25 tattoos in their life and they're 50 years old, right? What number would you plug in? It's not gonna be the 25. They're 50s, and every decade they've got another 10 tattoos, right?
Mhm.
About 5. 25 is the number you would put in for X, right? So you get 5 tattoos per decade,
Okay,
on average, assuming it's continuous. People
but
do
that,
that.
you wouldn't ask us a question like that.
I would simply say watch your units. Right? Each X predicting Y, X will come in the form of a specific number of units. If you're given a different number of units for your X value, you're gonna have to convert your X value to the units that are originally in the equation that the line predicts.
Can you say that again?
Please, and like,
If, let's say, I say X is number of something per hour, right? If I give you number of X scores in minutes, right? Do you plug in the number I give you, right? Or you plug in something else, what would you use if I give you the units in minutes, and the original linear regression is in the form of an hour,
we
right?
have to convert minutes to hours.
You have to convert minutes to hours, right? Does that make sense?
Yeah.
If I give you something like number of inches is my X score from the linear regression, so the linear regression calculates Y predicted from 0.64 inches of X. That right? If I give you X in feet, right, you'd have to divide it by 12. You multiply by 12 to get the number of inches as a predictive score, and plug in multiplied value in inches.
So we'll have to know inches and centimeters and all that?
No.
Okay, I was like, oh, we know all that.
You will not have to know any metric calculations in that regard.
Okay.
But I do want you to pay attention to the units involved, because the main point, it's not worth a lot of money, but there's at least one question that's going to do this. At this level, students are so in the habit of, here's the equation, plug in a number. Here's an equation, plug in a number. And at one level, you have to realize the numbers represent actual data in the real world. It's not as simple as plugging in the numbers. It's more in terms of you have to recognize what do those numbers mean,
Right.
right? So there's at least one question where you have to make a minor conversion, but it'll be well identified in the equation, right? In terms of where the units change.
Okay. Mhm. So you went over everything that's gonna be on the test? You went over everything that's gonna be on the test? as
3
far as
major
you know?
sections, Z-scores, linear regressions, correlation coefficients. Keeping in mind there will be a page of multiple choice questions dealing with the assumptions and the background information for each of those topics.
That just confuses me just a little bit. Okay, but Z-scores is continuous data, R-scores is generally discrete. Standard deviation, we need to know how many single points away from the mean. We need to know that standard deviation is,
Standard deviation is on average how far away is a given score from the average. How far away is a given score from the mean. Right?
okay.
That would be in standard deviation units, or when you do Z-scores, Z-scores are in standard deviation units.
points, less fit from the line, and your regression characteristics of the Z-score, stuff like that.
Characteristics of correlation coefficients.
Characteristics of
Well,
correlation.
the Pearson product moment.
Oh, or what?
The one correlation coefficient we dealt with is the Pearson product moment correlation coefficient. There are other kinds of correlation coefficients, all of which measure the degree of association, the measurement of associations, but they rely on different underlying assumptions, mostly with regard to scales of measurement. So if you got something like ordinal data, you can do a Spearman rank order correlation coefficient instead of the Pearson. If you got nominal data, you do something like a point biserial or a phi correlation coefficient. I'm pretty sure phi is the right statistic. I don't remember on that. I never use it. Nobody ever does.
Way better, I got it now.
Is that right?
Yes. Mhm. It is one of the. I need to write down that. And I guess that's real hard on the, identifying the formulas.
You will be given all the formulas all on top of the board. Plus, you might have a
Knowing-
couple other distraction formulas. Yeah.
But I'm saying knowing what I need. But S is N minus one. The one with N minus one.
If you're calculating
Dang.
a standard deviation from sample data, the denominator has n minus one in it, yes. If you're
But
calculating,
this population is just N.
correct, I don't have that formula. It's, this is part of the equation right here, the denominator here. This will be, I'll put it in parentheses as well. That is the standard deviation for population data, which is sigma, which is this term.
Yep.
Is that okay?
Mm-hmm. London. Then you can't go to sleep in college.
I've got lots of students who do it.
No, you don't.
I went to last class, last week.
In your class?
Yeah. It was an evening class, so they're quite tired. There was a student fell asleep in class.
Do you wake them up?
Not specifically.
Wake me up if I ever do it because I can't miss a moment.
We're about done, so you can get ready to go.
You like this school?
I wouldn't either.
Me neither. Do you get it? I see you got your formulas.
Okay. I think I can just know, I just rewatched the video.
Another what, class? No, that's it. Wait, the other one. Oh, it's a 7 at? Oh, no, that's when I'm here by myself. Today I just came to get extra help. So today wasn't a real class. It's way more kids in here than this for people.
There are a few students.
They fill up all these chairs.
Not all of them, but a lot of them. Cause that's how she recorded the work. Instead of remembering everything, she recorded so that she can go home and look at it. That's a good question though.
Memorize it there.
Yeah. That's how I be in my truck. Sit in my truck when I'm getting unloaded and I watch the video.
But all college classes aren't like this. Some of them are really fun.
Do you have the homework answers on you today or not today?
For which? For the fourth or
For
third?
the fourth.
I know vaguely what they are.
Oh, okay.
I'm gonna go over it next class. I'm gonna Basically, everybody's here.
That's my pencil.
I know.
He's sitting right there.
Thank you.
And there's another
Mm-hmm. The only pencil I got.
with you.
With
For the maybe, I feel like as long as that one's bright, then I should know what we
No, those are all.
Oh, no, it's terrible.
As long as we're on that one.
Do I wanna go to work? That's a good question.
you say you got what?
Do I wanna go to work?
Where you working?
I work at M&M Cartage. I drive semi-trucks at night.
What the world?
Yeah.
Is it hard?
When I was over the road, it was fun because I got to see a lot of places. But in city is a lot of crazy drivers, so it gets stressful.
You feel comfortable about this, or you go still practice?
Semi, but I'm gonna watch the video to make sure what I was missing, I fill in those blanks. But most.